Hey everybody, welcome to another video, and actually the last video in Python for Linguists, at least for the time being. This one rounds up the introduction to regular expressions, and by rounds up I really mean it introduces quite an important new aspect that we haven't discussed so far. This is grouping. Grouping allows you to specify sub-patterns within a regular expression where you can do individual things to those subpatterns, which allows you to write the regex a bit more efficiently and flexibly. But perhaps even more importantly, it allows you to extract different elements of a relatively complex pattern in a systematic way. In tuple format, that's the reason I introduced tuples in the previous lecture, such that, for example, if you extract a complex linguistic variable like let's say future time reference, right, with will or be going to. You can write the regular expression in such a way that the first element in the tuple is always, let's say, the future time expression itself, will or going to, or maybe won't could be in there as well, or gonna. The next is something optional like negation, where you either have a not or a not in there or nothing at all. And the third is going to be the verb that's actually pre-modified by the future time expression. So you extract not just, you don't just find the individual variable you're interested in, but you actually extract all its relevant parts in an already very structured way, which is hugely helpful for further analysis. But this is getting a little bit ahead of ourselves. For the time being, we'll get to examples of this towards the end of today's video. For the time being, just remember there will be code examples and also exercises, so be ready to engage those. And once you are, we can get started in earnest. Here's a situation that we come across quite often in natural language analysis. Um, and that's different inflectional forms. Here, in this case, different inflectional forms of the verb be. There's lots of them, or a fair number of them, but for right now, let's think only about be, being, and been. So the bare infinitive, the present, and the past participle. And it would be nice to have some way of expressing be and then either that or optionally that followed by the string ing or the string en. And all of that followed by a word boundary. That would be one relatively concise expression that allows us to capture be, being, and been all at the same time. And we haven't learned how to do that yet, but obviously this is something that you can very much do with regular expressions. And for that, we need to establish grouping, which is done here in the second line of the code snippet. So a lot of this looks familiar, right? And what I want to focus on is the stuff in the parentheses. So we just start the raw string, which ends up being treated as a regular expression then, with a character sequence, nothing new there. And it ends with a word boundary. We've established that. And we have this question mark, which we've encountered, but we've so far only encountered it applied to individual characters, either a character or a set of characters within square brackets, but always a thing that is only one character long. With these brackets, we can turn this into a multi-character sequence, right? So anything within these brackets, the question mark applies to. And we have further internal structure here with this pipe character. That disjuncts basically between two options. So it's either the sequence ing or the sequence en is what all of this expresses. And then the question mark just makes the entire thing optional. So that means either just be or being or been, followed by a word boundary. This is precisely what we wanted. So that does the job. You can note also, and if you can follow along with what I'll explain now, then you're definitely on a good path. You can note also that we could have done simply opening parentheses right here after the opening quote marks, and then be, pipe, being, pipe, been, no question mark, word boundary. That would have achieved the same thing. This is just a little bit more concise in terms of how many characters it consumes. All right, and that's the basic logic here, and I'd like you to practice with this right away. Yellow snake time. So we've done this for be, being, and been, but could you please elaborate the pattern so that it will catch all inflectional forms of be, right? Is, are, were, was, etc. Um, this should work. Try to make this work in a sort of word list situation where you do a list comprehension and use RE match your expression word as a filtering criterion in that list comprehension to only keep words that are in fact inflectional forms of be. That's the base task that I feel confident you should be able to accomplish. Once you've done that, take the same regular expression and use it with re find all over like just one long text and sort of note the differences that arise. And then the bonus is really where it gets interesting. Try to find all instances of the progressive, um, here defined as any inflectional form of be followed directly by a polysyllabic word ending in ing. And polysyllabic, you can just take that to mean the word has either an A, O, E, I, U, or more of these preceding the ing sequence somewhere in the word, at least one of these. And if that's too tough, you can simply look for words ending in ing as well. It's going to catch a number of false positives like thing or king, etc. But not to worry about at this point. You'll need re find all for this because you're looking at a multi-word sequence. You can't really use a single word list or list of single words to do much with that. And so you need to figure out a solution for the behavior hinted at above. The solution can be accessed on the online slide if you scroll down. I'm not going to scroll down to it. I'll rely on you to pause the video, get going, and once you've either found a solution or you've um, you end up in a corner in despair, then you can look at the solution. What I do want to show, though, is the behavior of the solution. So let me quickly do just that. Switch displays here. So I prepared this in advance. I wrote the regular expression, and I also have a variable called SOU. That's all of the text of the State of the Union addresses. So I called the RE prog RE, and SOU is just these texts. And I verified this. It does basically what the prompt is asking. It results in a positive hit for any instance of be followed by a polysyllabic ing ending word. And this is what it gives us. All of these are correct hits, but what we get is not very informative, right? We get some form of be, is, are, were, etc. And then it's always tuples, and then mostly it's nothing towards the end of the tuple. And in some cases, it's either en or potentially ing, although I don't see an ing here. So this is behavior that we need to further have a look at. What's going on here? Well, the thing is, grouping actually does two things. The first thing is what we've talked about so far. It keeps things together so we can separate them with a pipe character and treats these as units that you can, either alternate between. So either run, walk, or stride in this regular expression below here. And you can also kind of apply a plus, a question mark, a curly bracket, etc. To the whole thing. So make the whole thing also optional or multiples of this. Think of opening parenthesis, HA, closing parenthesis, and then, I don't know, between 3 and 100, right? That catches all instances of ha, 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 and even more ha's. This is the sort of stuff you can do. That's what we focused on so far, but what's in B here is almost at least equally important. It constructs a group within the pattern to be matched, and that group is not just for internal processing, but it also has an effect on what gets returned, especially by re find all. So re find all actually only returns all of the groups defined in a regular expression. In tuple format, the regular expression itself, since it's always the same, always has the same number of groups, but some groups are very often empty, like the ing en in the previous example, right? It just returns an empty string. And this behavior can be a blessing and a curse. So we can have re find all, run, walk, stride, ing, um, being the regular expression, and then apply to he was walking and striding then running, and that will return walk, stride, run. And that makes sense, but probably in a context like this, what we're probably interested in is rather the full surface form, right? Running, walking, striding, or running, striding, walking, in whatever order you have here. So what can we do about this? One thing we can do is to modify this double behavior and actually turn option B here off. And we can do this in a slightly complicated way. Let's look at the code right away. It's largely the same code. re find all, r, opening parentheses, run, walk, stride, ing, /b, but it has a question mark colon immediately following the opening parentheses. And that is just the trick here, right? If we use that, this is the only difference. The re actually finds walking, striding, running. So appending question mark colon immediately after opening parentheses avoids the regex being treated as a group to be searched separately. The grouping behavior, right, to look for either run or walk or stride followed by ing, that remains. So the A part of the previous slide, that remains, but the B part is switched off. So that allows you to play around a little bit, and sometimes you want one, sometimes you want the other. We can also have several groups. We actually saw this in the example of the progressive RE that I just showed you, right? We found always an instance of an inflectional form of B, and then as a second thing, usually an empty string, sometimes ing or en. So let's look at something a bit more applied. We have a match object called match object, and it matches the pattern alphanumeric character sequence space alphanumeric character sequence space alphanumeric character sequence. And the three alphanumeric character sequences are all turned into groups. And we apply this to find these words. And if we do match object dot group, so just kind of the overarching group, it actually gives us the whole thing back, find these words. But it also has internal structure. Group 1, group 2, group 3, we get find these words. What's important here is that the general behavior of match object basically is it's able to return the whole match for the whole regex string, right? It also includes the spaces, which aren't part of any group. That's just the full match. And re find all works differently. If we do this re find all like this, it only returns the tuple find, comma, these, comma, words. That's a different behavior. If we, for example, if we appended question mark colon to the second one, it would not return find these words, but only find words, right? So with re find all, you never get, as soon as there's a group in there, you never get the full regex back, unless you wrap the whole thing or wrap a group around the whole thing. Then I suppose you do. And that's sort of this again. It can be a blessing or a curse, but understanding it allows you to extract meaningful stuff from a linguistic variable that you search with a regex pattern, while ignoring some of the stuff that maybe isn't so interesting. All right. I think I've covered this. I'll read it out once again. re find all will not return the string matching the whole pattern, as re match group would, but a tuple containing the matches for the individual groups in the order that they appear in the regex, always in that order, which is important, that the order is always the same, because that allows you to, again, deal with this in a structured way when you look, for example, at a linguistic variable. And whether to group or not to group, so whether to use question mark colon or not is the question here, can't be categorically answered, right? One isn't better than the other, but you need to understand what each does in order to write your regex in a way that it actually returns what you want. So here's one example. A search pattern relatively complex. I believe I've introduced this before, but since I'm not sure, the uh, backslash following a string is basically a forced line continuation character. So it means the string isn't in fact over, but it resumes in the next line, which is very helpful if we have long expressions that we want to keep some structure to not force all of this on one line. Um, so the search pattern here is how to or that followed by space. Backslash is just the line continuation, and then any non-space character, one or multiple times, followed by one or multiple spaces. So that's a word basically, right? Followed by of, followed by a space, one or more spaces, followed by an indefinite article, so a or n, right? The question mark turns the n optional, followed by a space, and then just a word, any sequence of non-space characters. What does this match? It's not a perfect expression, but it is pretty okay for a first stab at the construction how to that adjective of a noun, right? That great of a deal, too much of a good thing, etc., etc. And what we get here is the first group, how to that. So the head adverb we extract systematically, and then the adjective or whatever is following that, right? There'll be a couple of false positives, but I've checked it. It mostly gives good value, not too many false positives. And then off and an aren't returned. We're not interested in those here. Those are stable, so we don't need to wrap a group around them because they're always going to be the same thing anyway. And then the following thing, which we assume in most cases to be a noun. So too much thing. How big deal, etc. Right? And that gets extracted systematically. You can write that to a data table and then do some analysis with. And that's kind of the most mileage I've tended to get out of regular expressions. They're really quite cool that way. Sometimes maybe more easily written than some other code that would achieve the same thing. My experience is getting it 100% watertight isn't always easier than working with, maybe a word list and a bunch of if else, elif, else conditions. Um, but it usually at least gives a good first stab at the data. So I'd like you to practice on this sort of stuff as well. A relatively, multi-element construction that we want to systematically extract. And the yellow snake wants you to look at the way construction. Write a regular expression that you can use with re-find-all to extract all instances of the way construction. Those are constructions like she worked her way up the corporate ladder, he bumbled his way across the dance floor, etc. And try to extract the following elements as separate groups: the verb, the possessive pronoun, and the preposition following way, right? So re-find-all for these two, for each of these would give us worked her up, bumbled his across in these examples. You could try to do some other things. Way we don't really need because it's a constant, so we don't actually need to extract it. And the subject is a bit more difficult to get at. But you could try to just look at the word before the verb, or basically the word before two words before his way, her way, etc. But basically, these three elements is what I'm looking for here. And test this against some data to see how good it is. It's given the nature of the construction, it's never going to be completely watertight, but you can get pretty good results with this. Results where on a moderately large corpus, I think it would be reasonable to take these and then manually quickly exclude the false positives and really work with what you've got. That's the final exercise for this final lecture. We'll be doing a lot more practice on regexes in class. I'll see you then. And in the meantime, um, take to the air with these regexes. Time to soar. Here are my image credits. Thanks for tuning in. Links to the slides, also the QR code. It's all in the YouTube description as well. It's all here. See you soon. and thanks for being attentive listeners to this tutorial series. Goodbye.